Pipelines carry millions of barrels of petroleum and petroleum products. Petroleum and petroleum products that have many different qualities and properties. For example, gasolines of different octane ratings. Diesel fuels with small and varying amounts of sulfur. Crude oils of many different gravities and with small and varying amounts of sediment and water. The first step in determining the quality and properties of oil or products is to obtain or grab a sample. Then this sample can be tested and analyzed. But for the test to be meaningful, the sample must be representative. It must be an accurate representation of what is flowing in the line. In some cases, grabbing a representative sample is easy. If the properties of the oil or product flowing through the line don't vary, then a single grab from any part of the shipment is adequate. On the other hand, suppose the properties of the oil or product vary as it flows through the line. It could be a number of things, but let's say we're concerned with S&W content of oil. Maybe the oil starts with a lot of S&W, but as flow continues, the S&W content drops, then goes up again. In this case, frequent grabs must be made throughout the total batch. For example, in marine cargo sampling, where a large part of the S&W is concentrated in the line at the beginning of each discharge, one grab may be taken per 80 lineal feet of pipeline volume. Now, this is not a hard and fast number. It's just one example. In pipeline operations, where S&W content tends to be more uniform, one grab per 320 feet of pipeline volume may be adequate. Again, this number may vary depending on sample requirements. For more details on sample frequency and for more information on sampling in general, refer to the API Manual of Petroleum Measurement Standards, Chapter 8, Section 2, Automatic Sampling of Petroleum and Petroleum Products. Another problem in getting a representative sample has to do with the speed or velocity of the flowing liquid. For example, at low flow velocities in a horizontal line, denser components, and again let's say it's S&W, tend to settle. However, the sample probe, a small diameter length of pipe that grabs the sample, is usually placed near the center of the line. Now, with dense components like S&W concentrated near the bottom, a sample grab taken at center is non-representative. It contains less than the average amount of S&W. Now, to solve this problem, the stream must be adequately mixed. But how can the stream be mixed? Well, in several ways. For example, a pump can cause the stream to mix. So, if a sampling point is located just downstream from the pump may give the needed mixing. But beware. A pump can also cause a centrifuging effect, concentrating dense components, S&W in this case, near the sides of the line. So if you depend on a pump for mixing, verify your sample results. Another way to get adequate mixing is to install a length of pipe with reduced diameter in the line. Flow velocity increases through the reduced section. It's like all that liquid has to crowd together to get through it. So flow velocity increases. And when flow velocity increases, the flow becomes turbulent. turbulence helps to mix the stream. Typically, if the flow velocity is 8 feet per second or more, and light crude oil is flowing in the line, then this system should give adequate mixing. But a word of caution, this method creates a permanent pressure drop with wasted horsepower that can cost you money. A vertical piping loop can also provide mixing. As the flow turns the corners, turbulence occurs to mix the stream. In a vertical loop, a flow velocity of 5 feet per second or more may give adequate mixing. Also, if possible, locate the probe in the exiting leg of the loop. This takes advantage of all but one of the elbows for mixing. You shouldn't locate the probe downstream from that last elbow because some settling of heavy components could occur in the horizontal section of the line. Many other ways to get adequate mixing are available. You can get more details on types of mixing and minimum flow velocities for various densities of oil and product from Chapter 8, Section 2. So, samples can be grabbed and tested to determine the quality and properties of oil or product in a pipeline. But the samples must be representative. They must be an accurate representation of the oil or product flowing in the pipeline. To get a representative sample, the sample frequency must be adequate. For instance, in marine cargo sampling, where a lot of S&W is concentrated at the beginning of a discharge, typically 1 grab is taken per 80 lineal feet of pipeline volume. Or in pipeline operations, where S&W content tends to be more uniform, typically 1 grab per 320 lineal feet of pipeline volume does it. Also, mixing is important in obtaining a representative sample. To get adequate mixing, a pump can be installed in the line immediately upstream from the sample probe. However, a pump can cause a centrifuging effect too, so verify the results to make sure the pump is doing the job. A length of reduced diameter pipe can be installed to get mixing. Turbulent flow through the reduced section causes the stream to mix. If the flow velocity is at least 8 feet per second, then this system should give adequate mixing for light crudes. A vertical piping loop in the line can also cause mixing. Turbulence at the elbows mixes the stream. A flow velocity of at least 5 feet per second should give adequate mixing of light crudes flowing in vertical piping loops. Also, in a loop, locate the sample probe in the exiting leg of the loop to take advantage of the elbows. And finally, for more details about sample frequency and flow velocities for adequate mixing, see the API Manual of Petroleum Measurement Standards, Chapter 8, Section 2. If you have workbooks, stop the tape and work Exercise 1. Then return to the program. Now let's look at automatic sampling systems. Two types of automatic sampling systems are the inline type and the fast loop type. Basically, an inline system consists of a combination probe and sample extractor mounted in the pipeline, a controller, and a sample grab discharge line to a sample receiver. We'll examine these parts in detail in a moment, but first, look at this fast loop system. It consists of a bypass line that comes out of the main pipeline at the probe, a pump, sample extractor, controller, sample grab discharge line, and sample receiver complete the system. Now, this fast loop system utilizes an existing pump in the pipeline. The fast loop starts at the probe on the discharge side of the pump. The sample extractor is in the vertical section of the loop. The loop re-enters the pipeline on the suction side of the pump. Now, the main difference between the inline system and any fast loop system is in the probe and sample extractor arrangement. In the inline system, the probe and extractor are combined and inserted directly into the pipeline. In the fast loop system, the fast loop exits from the probe and a sample extractor grabs the sample from the fast loop. Given a choice, use the inline system because a fast loop system has a limitation. It grabs the sample out of the fast loop instead of directly from the pipeline. In effect, the fast loop system samples a sample, and representativeness can be lost. However, component location problems can make it necessary to use a fast loop system. So if you have to use it, install the probe where flow in the pipeline is well mixed. Here, the pump in the pipeline should give good mixing. But remember, pumps don't automatically ensure good mixing, so verify the results. If the fast loop can't be installed around an existing pipeline pump, then a pump in the fast loop itself may be needed. The idea is to keep flow velocity in the fast loop high enough to duplicate flow conditions in the mainline stream. Now let's look closer at components of automatic sampling systems. Using an inline system, let's begin with the combination probe and extractor. The combination probe and extractor mounts directly into the pipeline. Usually, it extends to the center of the line where the most representative sample can normally be grabbed. When actuated by a signal from the controller, the sample extractor closes an internal chamber. This chamber captures a grab, typically about 1.5 cc in size. Each grab is displaced through the discharge tube to the sample receiver. The controller is an important component. It operates the extractor. That is, it automatically opens and closes the extractor so that it grabs a sample from the pipeline at regular time or volume intervals. Now, if the controller operates the extractor at volume intervals, the sampling is said to be flow proportional. In other words, the controller is paced by a flow sensing device in the pipeline. The flow sensing device, through the controller, operates the extractor each time a measured volume flows past the sampling point. For example, here the controller actuates the extractor every time the volume contained in 320 feet of pipeline flows past the sampling point. If the controller operates the extractor at time intervals, the sampling is said to be time proportional. In other words, The controller is paced by a timing device. The timing device connected to the controller operates the extractor at selected time periods. For example, here the controller actuates the extractor 900 times per hour. In general, time proportional sampling is used when the line flow rate is relatively constant. On the other hand, flow proportional sampling is used where the flow rate is not constant. Whether the automatic sampling system is flow proportional or time proportional, failure alarms are needed to warn of malfunctions. Otherwise, non-representative samples, or no samples at all, may result. And remember, alarm mechanisms may also fail, so there's no substitute for the human eyeball. Frequent visual observation by measurement personnel is a good way to maintain a successful system. The next component of the automatic sampling system we'll look at is the sample receiver. But before we do, let's quickly review what we've learned in this part of the program. Two types of automatic sampling systems are available: the inline type and the fast loop type. The main difference between the two systems is that in the inline system, the probe and extractor are combined and inserted directly into the pipeline. In the fast loop system, the probe and extractor are separate so that the extractor grabs the sample from the fast loop. Now, the fast loop system is okay, but bear in mind that it samples a sample, and representativeness can be lost. Make sure adequate mixing is maintained in such a system. The controller in the automatic sampling system operates the extractor. It can be paced to operate the extractor at volume or time intervals. If the controller operates the extractor at volume intervals, the sampling is flow proportional. In other words, the controller is paced by a flow sensor in the pipeline so that a sample is grabbed each time a measured volume passes the sampling point. Now, if the controller operates the extractor at time intervals, the sampling is time proportional. That is, the controller is paced by a timing device so that the extractor captures a sample at selected times. Time proportional sampling is used in lines where the flow rate remains relatively constant. Whether flow proportional or time proportional, failure alarms are needed for any automatic sampling system. Otherwise, non-representative samples, or no samples at all, may result. And finally, remember that there's no substitute for vigilance on the part of personnel in case the alarm system fails. If you have workbooks, stop the tape and work exercise 2. Then return to the program. Now let's take a close look at the sample receiver, the container that holds the captured sample grabs. First, sample receivers should be the right size. They must be big enough to contain a representative portion of the total volume delivered over a period of time. Procedures for calculating receiver size are detailed in the API Manual of Petroleum Measurement Standards, Chapter 8, Section 2, automatic sampling of petroleum and petroleum products. Sample receivers can be permanently installed and can be single or multiple units. Multiple units are used when different crudes or products are sampled and it's necessary to isolate them. Portable sample receivers are also available in both single and multiple units. All sampler controls and access or withdrawal points should be sealed to disclose any tampering. The quality of the oil or product greatly influences volume determination, specification compliance, and in some cases pricing. So security is important. Piping from the sample extractor to the receiver must slope continuously downward without low spots so that all the captured sample drains into the receiver. The receiver should hold the sample under enough pressure to minimize vapor losses. The receiver must have a sloping bottom to aid in mixing and draining it. The inside of the receiver should be coated with a smooth acrylic or phenolic paint. This minimizes corrosion, incrustations, and water clingage. Inspection closures should be at least 8 inches in diameter to make it easy to clean the receiver. No sample piping should be connected through the closure. Quick opening closures should be provided on receivers. The receiver must be thoroughly cleaned between shipments, and a quick opening closure makes it easy. A full-length gauge glass, protected to avoid breakage, should be provided to let you know that a sample is being collected and help avoid overfill problems. A pressure relief valve should be included to maintain enough pressure in the receiver to minimize evaporation loss. Normally, it's set at about 10 psi, but don't set it so high that the sample can't enter the receiver. A vacuum breaker allows you to drain the receiver while it's closed. The breaker provides a vent to the atmosphere that breaks the vacuum inside the sealed receiver. A pressure gauge is required on receivers to indicate that all openings are properly sealed and the pressure relief valve is working properly. You also may need to insulate and heat the receivers. Now, this depends on the operating conditions and the material being sampled. If you're using portable receivers, they should have a few additional features. Features like carrying handles, quick opening, removable covers, quick release connections, and security seals. Also, they should be light in weight. Whether the receivers are portable or fixed, the sample inside needs to be properly mixed to ensure dispersion of free water and to eliminate stratification. Otherwise, a misrepresentative test may occur. So, the sample receiver must be equipped with an effective power-driven mixing device. Hand-driven pumps or hand-driven mixing devices won't do the job. Few hand-driven devices are ever operated long enough to be really effective. One type of system uses a pump to extract the oil from the bottom of the receiver and re-inject it vertically downward from the top through a perforated pipe. Another type uses a pump to move oil through horizontal spray bars. Either horizontal or vertical bars help mix the sample. Sample draw-off may be taken from a valve in the discharge piping or from valves in the side of the receiver. Samples from 2 levels of the receiver permit comparing results for adequate mixing. Arrange the piping so that there are no low spots that could trap S&W. The piping should also permit complete drainage of the receiver the circulating pump, and the piping itself. With suitable valves, the circulating pump can also be used to pump excess sample back to the pipeline or to a sump after the portion needed for testing is drawn off. A less desirable way to mix the sample in the receiver is to use a motor-driven impeller. Taps located at different levels must be used to draw off samples into centrifuge tubes to determine proper mixing. In addition to good sample mixing, good sampling procedures are a must. Let's go over a few. To begin with, make sure all security seals are intact and that the sample has not been tampered with. Make sure the flow velocity of the stream is adequate. A stream flowing at less than the recommended minimum velocity will require some type of mixing device upstream of the sampling location, such as tees, elbows, or power or static mixers. The sampling frequency must remain constant during a sampling period. Changing the frequency affects the accuracy when sampling a variable stream. Samples must be withdrawn and tested before you remove any other liquid from the sample receiver, and take the test portion only after all of the sample is thoroughly mixed. Purge the draw valve and piping before you take a sample. Also, don't let any rain, dirt, or condensation into the sample receiver. The sampler should operate at all times when oil or product is flowing in the line. And conversely, the sampler should not operate when the stream is not flowing. Don't leave solvent in the receiver, pump, or circulating line. Any leftover solvent contaminates the next sample, so purge all solvent. Avoid low spots in the tubing from the sample extractor and in the circulating line. Water, sediment, and solvent can collect and remain in any low points. If possible, draw samples directly into the glassware in which tests are to be conducted. You can foul up even the best sampling system if you mishandle the sample. So, if you have to transfer the sample into another container, try to minimize the number of times you do it. Also, get the sample to the lab as soon as possible to minimize settling time. Further, the lab should have mixing facilities to duplicate the mixing system you use at the sampling site. Now let's review. Sample receivers can be fixed or portable in single or multiple units, but whichever. All sampler controls and access or withdrawal points should be sealed to prevent tampering. Discharge piping from the extractor to the receiver should slope downward. Keep pressure in the receiver to prevent loss of light ends. The receiver should have a sloping bottom, and it should be coated with acrylic or phenolic paint inside. Use the gauge glass to determine if a sample is being collected. A pressure relief valve should be installed on the receiver to protect it and maintain enough pressure to minimize evaporation loss. Use a power-driven mixing device to properly mix the sample. Arrange all piping so that there are no low spots that could trap S&W. Make sure the flow velocity of the oil or product in the main flow stream is adequate, or proper mixing is provided. If it isn't, do not take a sample. And finally, if possible, draw samples directly into the glassware in which the tests will be made. Otherwise, keep sample transfers to a minimum. Don't mess up a good sample by poor handling. Properly installed and maintained automatic sampling units provide accurate and representative samples for testing for impurities in oil or product and for testing the quality of oil or product. With care on your part to ensure that the equipment is operating properly and that samples do not become contaminated, an automatic pipeline sampler is a very efficient way to obtain oil or product samples. If you have workbooks, work exercise 3.